time for us to go to the extremes. We're going to be looking for absolute max and absolute min. And in particular, absolute max and absolute min when our domain downstairs is a set which is closed and bounded, because we're guaranteed that they exist. Now the procedure is quite simple, really. Just remember the song. We're making a list, checking it twice, gonna find out which points are nice, right? And once we do that, absolute max and min will be found. So there is some practice because there are some details, especially as we start to go through the process of making the list. A lot of patience because there's oftentimes lots of boundary to check. And so it's not that any one part is hard, it's just there's a lot of little parts to keep track of. So practice, practice, practice. If you're following along with the video, make use of the pause button. See a problem? Pause it. Try it yourself first and see how you do. And then once you're finished, go ahead and unpause and we can compare answers. Well, let's begin. Our first problem. Find the global max and the global min for the function x squared plus 2y squared minus xy minus x minus 3y, and the domain 0 less than or equal to x less than or equal to 5, 0 less than or equal to y less than or equal to 3. Now global max and global min is just another way to say absolute max and absolute min. And so it just means the largest we could possibly be. Well, let's start by getting an idea of what our domain looks like. So it's in the plane, because our inputs, see, two inputs, so it's a two-dimensional thing. And we're told x goes from 0 to 5, and y goes 0 to 3. Okay, so here we'll mark 5, here we'll mark 3, and so our domain, it's a nice rectangle. Great, good. And of course, it's not just the boundary, it's the whole thing. So what's the procedure? Well, our procedure is we need to make a list of points. What are the good points? In other words, the points where we might have a max or a min. So, well, we're going to end up with a list. We'll make our list here. And generally speaking, what I like to do is I like to say, okay, let's do the interior first. And then after the interior, the boundary, which I split up, I always put the corners in because corners can be tricky and they're easy to forget. That's why they're tricky. It's not tricky to find a corner, but it's tricky because if you're not paying attention, they might escape your field of vision. So that's why I say make the corners first and then do each bounding edge. Or it could be a bounding curve. It doesn't really matter what we call it, but all right. So let's go through one by one. So let's start with the interior, because the interior, it's pretty simple. It says, look, where does the gradient equal 0? That's the real question. Where the gradient equals 0, that's an interior point. So we say, okay, in our case, take the derivative with respect to x. We'd get 2x minus y and minus 1 equals 0. And then take the derivative with respect to y. That's 4y minus x minus 3 equals 0. And when we say equals 0, what's really going on here is we say, look, there's the f sub x and there's the f sub y. So we're saying our partial derivatives, both of them equal to 0. In other words, where does the gradient equal 0? Well, we can rewrite this. No real big surprise there. As what? Well, this becomes 2x minus y equals 1, and minus x plus 4y equals 3. Okay, so now we have to look for ways that we can combine things together and get some cancellation going on. And so, well, there's lots of ways we can go about doing that. Let's multiply this bottom equation by 2 and add together. Well, why? We get 2x minus 2x is 0x. Cancellation. All right. Then we'll get minus y plus 8y. That's 7y. Here we're going to get 1 plus 6. That's 7. All right. Well, that's good. That tells us y equals 1. All right. Plug that in. Say to that equation, 2x minus 1 equals 1. 2x equals 2. X equals 1. So, aha, that leads to the point 1, 1. Now, does 1, 1 make our list? And you're going to say, yes, it makes our list. And it's true. The answer is yes. But let's be careful. What do we need to check? Remember, we only care about points that are inside of our domain. So if we had a point that somehow ended up over here, outside of our domain, we'd say, look, not on our list. Forget it. Forget it. Is 1, 1 in our domain? Well, it's roughly here. In our domain, so it makes the list. So there we go. 1, 1. Okay, good. So we've done the interior. So therefore, we say, look, any other point has to be on the outer edge. Okay, well, let's do our outer edge. And remember, there's two parts. There's the corners. We're looking for sort of the things here where things are corners, where curves come together. So in our case, we've got 4 corners. We say, okay, well, where are they? Well, 0, 0. Here at x equals 5, y equals 0. Here is at x equals 0, y equals 3. And here it's at 5, 3. All right, good. So those have made our list. Okay, quite a list, but we're not done. We now need to go through each potential edge. So notice there's 4 of them. So we're going to be here a while. That's all right. We've got time. So here we go. Let's look at this edge. So when we look at this edge, what we want to do is we want to reduce our function from 2 variables to 1 variable. So we think about, well, what describes the bottom edge? Well, on the bottom edge, that would be where y equals 0. So we can say, okay, for the bottom, which is y equals 0, our function becomes f x comma 0, which would be x squared and 0, 0 minus x and 0, right? X squared minus x. Okay, now this is a function of 1 variable. So again, look for critical points. So take the derivative, 2x minus 1, and set that equal to 0, and we come to the conclusion x equals a half. So at 1/2 comma 0. So that's a point on our list from the bottom edge. Well, keep working our way around. Lots of edges to go. Okay, let's do our left. All right, what's true about our left? Well, that's x equals 0. Okay, so on our left, x equals 0, what happens? Well, our function becomes f of 0 comma y. So everywhere we see an x, we put 0. So we have 0, we get 2y squared, 0, 0, and minus 3y. All right, take the derivative. And we say, okay, that would be 4y minus 3, or y equals 3/4. So y equals 3/4, we put it right there. It's onside, it's in our domain. It's possible, by the way, that we could have gone a critical point over there, and if we did, we'd say, forget it, forget it. If it's not in our domain, it's out. All right, so we have another point, 0 comma 3/4. All right, well, 2 edges down, still 2 to go. Well, let's keep going. How about the top? up here, what do we have? Well, at the top, that corresponds to when y equals 3. So, the top, y equals 3. What do we have? Well, that's f of x comma 3. Well, okay, so everywhere where we see a y, we put 3 now. So we have x squared, all right, plus 2 times 9, so that's plus 18, minus 3y, or sorry, excuse me, minus 3x, because y equals 3, minus 3x minus x, that's really minus 4x, and then minus 9, because y equals 3. All right, take the derivative. That would be 2x minus 4. Set the derivative equal to 0. And we say, aha, that leaves us with x equals 2. So, that point right there. So that's at the point 2, 3. All right, well, one more edge to go. Okay, we're making good progress. What's our last edge? Well, it's the right. Choose the right. Okay, so this would be at x equals 5. Well, all right, we'll do it over here. So the right, x equals 5. And so our function becomes f of 5 comma y. Okay, well, what is that going to be? Well, 5 squared is 25. Then later on there's a minus 5, so that makes 20. Then we're going to have a 2y squared. Okay, that's great. And then we have a minus 5y minus 3y. Remember, we've already got the minus x, so that became part of the x squared minus x being 20. So anyways, back to here. Minus 5y minus 3y is minus 8y. So that along the top edge, our function behaves nicely like a function of one variable. And therefore, we can now take our derivatives and we say, okay, look, critical point, 4y minus 8 equals 0. Okay, which says y equals 2. Great. All right, good. Well, that would be, if y equals 2, it would be somewhere roughly there. But it is a point, right? It's a point that we have to consider. And therefore, it makes our list, so 5, 2. All right, barely squeezed it in, but there you go. Now it's kind of good to pause and just sort of reflect. Did we sort of capture everything that we should expect to capture? Well, what should be true? We should have checked the interior, said, okay, we did that, we got a point. We made sure we got all the corners, good, and we checked every single edge. All right. So we've made our list. Whew, what a list. All right. Now, what we know is that our absolute max and our absolute min, or if you like, the global max and the global min, they occur somewhere on that list. So what we need to do now is plug every single one of these points into our function. Now, some of these points are easier than others to plug in. For example, 0, 0, we're going to like that one. 0, 0, 0, 0, 0. Great. Good. Whew. Of course, some of them will not be so easy. Now, 1 and 1, that's not so bad. It just says, look, add up your coefficients. You get 1 plus 2 minus 1 minus 1 minus 3. Well, the 1 and the 2 and the minus 3 all cancel, so you're left with minus 2. Okay. Now, some you have to think a little bit about. 5, 0. Well, what can we do? Well, you plug in y equals 0. You have a lot of terms canceling. And you're left with 5 squared minus 5, 20. Oh, that's pretty big. How about 0, 3? Everything with an x goes away. 2 times 3 squared minus 3 times 3. That's 18 minus 9. 9. 5, 3. Well, what can we do? Well, we have to be patient, right? Or we can make it a little bit easier on ourselves. We say, look, it's on, for example, let's say we take, let's take the right-hand curve, right? So 5, 3, it's in that corner. So I can go into the right-hand curve and plug in y equals 3. So it's 20 plus 2 times 9 is 18, so 38 minus 8 times 3. It's 24. So if we take 38, subtract 24, we get 14. Okay, so 14. Good. All right. Now, we could have done a similar thing. We could have plugged in here, x equals 5. And what happens there? We get 5 squared, 25. 4 times 5 is 20. So you get 5. Add 18. That's 23. Subtract 9 is 14. Okay. Now, the edges. All right. 1/2, 0. I like just to come in, say, look, let's just use these pieces. 1/2 squared is 1/4. 1/4 minus 1/2 is minus 1/4, which is minus 0.25. Okay, 0, 3/4. Well, okay, so that one, well, maybe let's try not to do that one in our head, because we have some numbers we have to work with here. We have 2 times 9/16. Okay, well, 2 goes into 16, so this is really like 9/8. Then we're going to subtract 9/4. Okay, subtract 9/4. Well, this is negative 9/8, which is negative 1.125. Okay. It's not unusual to have a calculator available when you're doing this. So if you're like, wow, wait, we got to do all this in our head? Well, you use a calculator. Okay, 2, 3. I'm going to plug in 2 into here. And what do we have? Well, 18 minus 9 is 9. 2 squared is 4, so that's up to 13. Subtract 8. Oh, well, that's 5. Okay, it's 5. Great. And, well, we're almost done. 5, 2. So I'm going to come into here, plug in 2. 20. And then here, we'll have 2 times 2 squared. That's 8. So that's 28. Subtract 16. Okay, so that's 12. There we go, 12. Wonderful. So now we've made our list. We plugged every point on our list into our function. And finally, the last step. You know, if you think of the process, make your list, check out what happens on each point, and now we do the fun thing, which is we scan the list. And we're looking for, let's do our min first. For our min, what do we want? Well, we're looking for the smallest number. Not the smallest number in magnitude, but literally the smallest number. So if we're thinking about, you know, we have positive infinity and negative infinity. Smallest number just means most negative. Okay. So that would be -2. So our min is -2. Our max, look for the most positive number, the largest number. Okay, so 20. 20 is the largest number on the list. And we're done. Sort of that last step is kind of anticlimactic, right? Because you're going through all the processes, and you're like, wow, there's lots of steps. And then you get to the very last step and says, okay, what's the smallest number? All right, what's the biggest number? Okay, you're done. So the challenging part here, and I don't want you to panic, no one single step is challenging. It's just the challenging part of it is that there's many pieces. So this is really an important time to say, let's be methodical. Let's try not to get too far ahead of ourselves. Let's be patient. We'll work it out. Life is good. All right, well, good. One problem down. We're going to do a couple more. Because, you know, the more you do, the more comfortable we're going to feel. So, let's do another one. find the global max and the global min for the function x squared minus 4x plus 2y squared minus 4y plus 1 for the domain, which is a triangle. The vertices at 0, 0, 3, 0, and 3, 3. So we should probably start by getting a sketch of our domain. So we know it's a triangle. The clue that it's a triangle is where it says it's a triangle. So that's a pretty good clue. I like that clue. And, well, we know the corners. 0, 0 will be here. 3, 0, that says x equals 3, y equals 0. That would be here. And 3, 3, that would be up here. So there we go. There's our triangle. All right. Well, one thing that's for sure, we have one less side to worry about. That should make this problem easier, right? At least compared to, say, a rectangle. A rectangle, you'd have to worry about 4 sides. A triangle, you have to worry about 3. All right. Well, let's go through the steps. Well, we know we need to make a list. So here's our list. And let's start with the interior. Okay, so our interior says what? Well, we're going to set our gradient of our function, in this case it's g, equals 0. So we take the partial derivatives, g sub x, 2x minus 4. All right, set that equal to 0. G sub y should be 4y minus 4. Set that equal to 0. Well, I think these can be solved. In fact, look, there's really no interchange between x and y. So it says, hey, x equals 2 and y equals 1. 2, 1. Good, good. Well, progress, right? Yeah, of course. It's progress. It's good progress. We now know where to look on the interior. Well, let's be careful. Does the 0.21 make the list? Well, we need to check. So if we sort of add some grid markers here, just to help us see what's going on, we would see that 2,1 is that point right there. It is in our domain. So it does make the list. All right. Well, good. Next up, the corners, right? Think about interior, corners, and bounding curves. Corners, they're pretty easy. We can spot them. And they're actually, were already given to us. It's these pieces right here. So we have 0, 0, 3, 0, and 3, 3. All right, good. Woohoo! Corner's done. Now, the bounding curves. Well, gotta work through it. Let's start with the bottom curve. Now, what's true about the bottom? Well, on the bottom, that's y equals 0. So, we can say what? Well, we make it y equals 0. All right, so for the bottom, y equals 0. And what happens? Well, our function becomes g of x comma 0, which is x squared minus 4x, 0, 0, plus 1. All right, take the derivative. G, well, I won't call it g prime because technically, all right, but take the derivative, and what do we end up with? 2x minus 4. Set that equal to 0, and we say, aha, that leads us to x equals 2, which would mean there. Well, that's in our domain. Makes the list. Okay, so that's at 2, 0. Good. Well, next up, we need to go to, say, the right-hand side. By the way, it doesn't really matter the order in which we do the edges. We just have to make sure we do all the edges. So, for the right-hand side, what's that? Well, x equals 3. Okay. All right, so we say x equals 3. And, okay, so we're going to have our function becomes g of 3 comma y, well, there's a 2y squared minus 4y. That's great. And then we get 9 minus 12 plus 1, right? 3 squared, 4 times 3 plus 1, which would become minus 2. Well, good. Plugging in, well, take the derivative. 4y minus 4, so that equals to 0. That gets us to y equals 1. All right, so that would be the point 3, 1, which would be here. Well, that's part of our domain, so it also makes the list. Now, that leaves us with one more side. And, well, which side? The slanted side. So we can call it Mr. Slanty. Okay. Well, you don't have to give it such a cute name. You can call it whatever you want. But the point is, there's one side left. How do we handle it? Well, we look at it and we say, okay, what's true about that curve? Well, what is that curve? And you can imagine, of course, it extends. Think about, well, what is it? It's a line. Which line? It's the line y equals x. And here we say, oh, perfect. Well, that's super easy. We can rewrite it as a single variable because what I can do is I can replace either y by x or x by y, either way, and life is good. So, well, let's suppose we replace y by x. Then what we have is we really have the function g of xx. Okay, well, that would be x squared and 2x squared, which would make it 3x squared, minus 4x minus 4x, which would make it minus 8x, and plus 1. Okay, well, take the derivative, and what do we get? 6x minus 8 equals 0. Or, well, you can divide it by 2. 3x minus 4 equals 0, which says x equals 4/3. Now, once you know x, you know y. And so we say, this corresponds to the point 4/3, 4/3, which would be here. All right, that makes our list because it's part of our domain. And now we're done with the list. We checked the interior. Yep. Got the corners. Yep. Checked each side. Our list is done. What's next? The last thing to do is plug in. Well, I should say the second to last thing, the last hard thing to do. And, okay, so we're going to plug everything in. Okay, so we're plugging everything into our function g. G, 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 G. Okay, when you plug in 2, 1, well, all right, that'll be 4 minus 8, that's negative 4, plus 2, it's negative 2, minus 4, okay, that's minus 6, plus 1, I think that's minus 5, is that, okay, double check, right? 4 minus 8 is negative 4, and then have plus 2, minus 2, plus 1, minus 1, minus 5, yeah. I feel good about that answer. Okay, 0, 0. Thank you, 0, 0. I always love working with you. 0, 0, 0, 0, 1. It's 1. Good. 3, 0. All right. Well, what would that be? We're going to get 9 minus 12. That's negative 3. 0, 0 plus 1. So that'd be negative 2. 3, 3. 9 minus 12. Okay, still negative 3. Here, you're going to get 18 minus 12. Well, that's 6. So you get negative 3 plus 6 plus 1. So put that together. Negative 3 plus 6 plus 1 is 4. All right. Good. Now, what's next? Well, next up, we need to take a look at, sorry, I'm just dramatically pausing. Always paranoid. This is the part, it's easy to make a small mistake in computation. And you always feel bad because it's like, I know the process, right? Why is it when I know the process, I make small mistakes? So that's why it's okay to take your time. There's not a prize for being the fastest. The prize is for being right. So you want to make sure you're not making too silly of mistakes. Okay, 2, 0. Well, I can just plug 2 into this part. 4 minus 8 plus 1. Well, okay, that's not so bad. 4 minus 8 is negative 4. Add 1 is negative 3. All right, great. Now, 3, 1. Well, I can plug 1 into this expression. 2 minus 4 minus 2. Well, that'd be negative 4. Okay, all right. Now, 4/3, 4/3. Let's be careful here. The way we can compute it is we can actually use our formula over there. So let's do that. Okay, so 3 times 4/3 squared, that's 16/9 minus 8 times 4/3 plus 3. Now notice we can cancel a 3 there. That's good. So we have, what is that? 16/3. So put everything over 3. 16/3 minus 32/3. Now this plus 3, we'll convert it into thirds, so that's 9/3. 16 plus 9 is 25. Subtract 32. 25 subtract 32 would be 17. Wait, no, that's not right. 7. Yeah, that's right. 7/3. Okay, so minus 7/3. All right. Well, great. What does that mean? Well, what does it turn into? Minus 7/3 is minus 2.33, so forth and so on. All right, so there we go. There we go. Now we're ready. We've done the work. We've done the work, and we can take a look and ask ourselves the question, where's the smallest numbers? Where's the largest numbers? And that'll give us our answer, absolute max and absolute min. So what comes out here? Well, when we look at the largest, 4. Okay, that's the largest number. So our max is 4. All right, what about the smallest? No, negative 4, that's pretty small. Aha, negative 5. Yeah, so our min is negative 5. And there you go. That's it. That's the smallest we can possibly be. Well, the smallest and the largest. So it says that our function, when we restrict ourselves to be just on top of this triangle, is always going to stay between negative 5 is the lowest and 4 is the largest. All right, good. Well, that was fun. So let's keep going, right? More problems. Hey guys, I can't believe it. I was trying so hard to pay attention and I made a silly mistake. I know. The good news is the answer is still right. So woohoo! Yay for us. The silly mistake was, look, the 3, look, it's 3x squared minus 8x plus 1. So where was that 3 coming from? Really, it's 3/3. So that isn't a plus 9. That's a plus 3. Okay. Well, how does that change things? Well, it becomes 16 plus 3, which is 19, and subtract 32/3. So if you take 19, subtract 32/3, you end up with minus 7/3. You end up with what? Minus 13/3. Okay, so this should have been minus 13/3, which is negative 4.33, so forth and so on. All right. So there you go. Now notice, again, it's still bigger than negative 5. So the min is still negative 5. If anything, we should have been suspicious because look at the point. See, it's close to the point 2,1, and therefore the value at 4/3 should have been close to negative 5. So given that we were kind of far off, that should have been a sign that, oops, go back and check your work. Well, anyways, glad we got it fixed now. Good, good. Well, it goes to show you, be careful. It's not the big calculus idea, it's the arithmetic idea that often stumps us. All right. The more that we do, the better we'll get. And hopefully we'll get so good we learn to stop making small mistakes. You know, that's the dream. Ah, the dream. So our next problem. Find the absolute maximum and minimum of this function. F of xy is 2x squared plus xy minus 5x plus a half y squared minus 2y plus 4 on or inside the triangle with vertices at 0, 0, 2, 0, and 0, 2. Okay, so let's sketch. We know it's a triangle. Aha, because it tells us that. And we can actually mark it, right? Where are the vertices at? 0, 0. Nice. It's always nice to get the origin involved. Okay, 2, 0 would be over here. 0, 2 would be up here. So we get a nice triangle sitting there. And it says, of course, it can be on or inside. Okay, good. So we look and we see, of course, one thing we should always sort of mentally check is this a nice closed and bounded region? In other words, you know, to ask if it's bounded, you know, could we imagine putting it inside of a big circle? So is there some big circle that everything can fit inside? And yeah, it's not so hard to draw a big circle here. And does it include its edges? Yes, because we're allowed to be on the edge of the triangle. So that means it's closed. Okay, well, now we know our process. And it's our making our list. Good. So hopefully we're going to get great at this process. We've been doing it a couple of times. And of course, the more we do it, the better we become. So let's start with the interior. Where do we go? Well, we set our gradient equal to 0. That's how we figure out what's happening on the interior. So f sub x, well, that's 4x plus y minus 5. Okay, set that equal to 0. F sub y, well, that would be x plus y, that one there, minus 2 equals 0. All right, now we have two equations, two unknowns. So let's see what happens. Well, we can write this as 4x plus y equals 5, and x plus y equals 2. And if we just do a quick subtraction, we'll see, aha, 3x equals 3, which tells us x equals 1. But if we know x equals 1, since x plus y has to equal 2, that tells us y equals 1. So we get the point 1, 1. Now, does that get into our set? Let's be careful. Okay, where is 1, 1? So if you put grid lines here, what you'll see is that the point 1, 1 is actually on the boundary. So yeah, it's definitely going to be in our set. Okay, so we'll throw it in. All right. Now, technically speaking, you could say, look, it's not in the interior, I'll ignore it. And you could say it'll show up when we get to the boundary, but the fact that it shows up on the boundary says, look, as long as it's inside the domain, you should throw it in. Life is good, right? Okay, the actual boundary points. Well, those are not so bad. We have 3 of them. So throw those in. 0, 0, 2, 0, 0, 2. And now we'll do the three sides, right? Because there's three of them. Okay, so we'll just work through them one at a time. Start here with the bottom side. Well, the way to describe that is y equals 0. So for the bottom part, y equals 0, we have that our function becomes f of x comma 0. Okay, so anything with a y goes away. So there's a 2x squared. Then there's a minus 5x. And then there's a plus 4. Okay, take the derivative. 4x minus 5 equals 0. X equals 5/4. So this would lead to the point 5/4 comma 0, which would be right around here. That's in our domain. It makes the list. Okay, 5/4 comma 0. All right, now let's do, say, the left-hand side. All right, well, what happens there? On the left-hand side, we have x equals 0. Okay, so we can say that our function becomes f of 0 comma y. Okay, so everything with an x goes away. So it's a half y squared minus 2y plus 4. Take the derivative, y minus 2. Set that equal to 0. And we end up with y equals 2. Well, so where is that at? Well, that's at the point 0 comma 2. It's here, already on our list. So we're good to go. We don't need to put it on our list again. So great. All right, well, that leaves us one more side. Okay, this side, well, this will be probably the most fun. It's the slanted side. So what we need to do is find a way to describe the curve. We can do it in many different ways. We can do parametric, for example, or we can say, oh, can we write this as a simple y as a function of x or x as a function of y? In this case, we can see it's a line. We see the intercept here is at 2, and the slope, well, we went down 2 over 2 is negative 1. So this is the line y equals 2 minus x. Okay, so for Mr. Slanty, now I should apologize because this sounds like I'm being biased. There can be a Mrs. Slanty as well. I don't want to imply that all slanted lines are always male. It sounds like a fun, cute name. Mr. Slanty. All right, slanted line, slanted face, whatever you want to call it. So y equals 2 minus x. Okay, so what we can say is our function becomes f of x comma 2 minus x. Oh, this should be interesting. So equals, so everywhere, well, let's just work it out, right? 2x squared plus x times 2 minus x, okay, minus 5x plus 1/2 2 minus x squared minus 2 times 2 minus x, and plus 4. Okay, that's the function. Well, let's keep cleaning it up. Okay, so what would that become? Well, this would be 2x squared plus 2x minus x squared minus 5x. And here, if you squared, we'd have 4 times 1/2, that's 2. Then you'd have a minus 4x times 1/2, that's minus 2x. Then you'd have x squared times 1/2, that's 1/2 x squared. Then minus 4 plus 2x plus 4. Okay, wow, we are, okay, equals. Okay, we're still cleaning up our function. Sometimes it takes a while to rewrite our function in a nice way. So let's see what we have. What are our x squared terms? Well, there's a 2x squared, a minus x squared, and a 1/2 x squared. So if we put those together, that would be a 3 halves x squared. Okay? So that gets those x squared terms. We have a plus 2x, a minus 5x, a minus 2x, and a plus 2x. Well, the plus 2x and minus 2x we can think of as canceling. 2x minus 5x is minus 3x. And then we have a minus 4 and a plus 4 that cancels, and a plus 2. All right, so there we go. Now, that's what the function looks like on the line, but we're after the critical points. So, taking our derivative, what does this become? Well, it becomes 3x minus 3 equals 0, which leads us to x equals 1. Of course, if x equals 1, what does y equal? 1. And so we get back the point 1, 1, which is already on our list. Oh, nice. Oh, wow. This was so nice. It turned out we actually only ended up with 5 points on our list. It's so beautiful when things simplify in a nice way. Okay, but we're not done yet. We've made our list. We make sure we look for everything. We check the interior. We got the corners. We check the bounding curves. Good. Now I need to plug these points in. So some of these won't be so bad, and some of them will be a little bit, we've got to take our time, but let's start with 0, 0. 0, 0, 0, 0, 0, 4. Oh, yeah. 0, 0. You're a great one. 1, 1. Well, that's not so far off either, right? 2 plus 1 minus 5 plus a half minus 2 plus 4. Okay, well, we went a little bit quick there. So what do you see? See, you have a minus 5 and a minus 2. That's minus 7. 4, 1, and 2 is positive 7. So that cancels, and you're left with a half. So at 1, 1, we get 1 half. Okay, so there we go. Good. Well, 2 comma 0. What would that be? Well, we can actually plug 2 into this expression. 2x squared minus 5x plus 4. That would be 2 comma 0. That would be 8 minus 10 plus 4. 12 minus 10 makes it 2. 0 comma 2. Well, that's like plugging 2 into this expression. And you notice minus 4 plus 4 is 0, and a half times 2 squared, well, that's a half times 4, which is 2 again. Oh, okay, well, that's kind of nice. All right, that leaves us with one last point. 5/4 comma 0. Well, okay, so plug in 5/4 into there. That one probably we want to be careful not to try to do it in our heads. Okay, so that'd be 2 times 25 over 16 minus 5 times 5/4. Okay, so that's minus 25 over 4, and then add 4. Well, of course, 2 goes into 16 8 times. So if we think of this as in terms of 8s, we have 25 over 8. 25 over 4 becomes 50 over 8 subtracted. And then 4 becomes 32 over 8. All right, so 25 plus 32 would be 57. Subtract 50 leaves us at 7/8. Okay, 7/8, which I think is 0.875. All right, good. Well, what do we do? What we do is we now take a look. And we say, all right, well, among these, which one is the smallest? Which one is the largest? So, scanning for the largest, okay, pointing us on 5, 2, 2, 4, a half. Okay, 4. That's the largest. So, our max is equal to 4. All right, which one's the smallest? Well, 1/2 is 0.5 and versus 0.75. Okay, 0.5 is going to be smaller. And everything else is certainly bigger than 0.5. So the min is a half. And we're done. Good. Good. Ha! We're doing pretty well. We're kind of speeding up now. Once you get the hang of it, they go kind of smoothly, right? It just flows in a natural way. All right, well, let's keep going. More problems. Always more problems. So, our next one. Find the global max and the global min for the function h of xy, which is 2x cubed plus 3y squared minus 12x, where the domain is x squared plus y squared is less than or equal to 4. Oh, well, that doesn't sound very triangle-like. Well, what's going on here? Well, if we sketch x squared plus y squared less than or equal to 4, it's a circle. It's a circle of radius 2. So, there we go. Okay. And, of course, x squared plus y squared less than or equal to 4. The equals 4 is the outer part. The less than is the interior. So, all right, great. So, that's perfectly fine. We can consider regions like that. They're allowed. We're allowed to do this. Of course we're allowed. Of course we're allowed. Well, we have to think a little bit because it's slightly different than what we've done before, but let's go through our procedure. Okay, first part is interior. So for the interior, all right, what would that be? Well, gradient of our function, in our case h, equals 0. Okay, so take the gradient. We want to look at h sub x, h sub y. H sub x, 6x squared minus 12. Set that equal to 0. H sub y, 6y. Set that equal to 0. Oh, well, actually, 6y equals 0. Okay, that tells us that y equals 0. All right, no problem. What about x? Well, 6x squared has to equal 12. That really says, look, x squared better be 2, which leads us to x equals plus or minus square root of 2. So we're getting two possibilities. All right, so what do we get? Well, when it comes to our list, they're both going to be in there. So we're going to have a plus the square root of 2, comma 0, and minus square root of 2, comma 0. And if you look at square root of 2, we should have pointed out that our radius here is 2, means we're going 2 in each direction. And the square root of 2, it's actually smaller than 2. It's 1 point something. Okay, so we have these 2 points. All right, good. Now, that's the interior. Done. What's next? The corners, right? I always like to think, okay, interior, corners, and then bounding curves. Okay, where's the corners? there aren't any. It's all smooth. Ooh, it should be interesting. Okay, all right. So no corners. That's okay. That's okay. Now, the bounding curve, the circle. All right, so we have to think about what's happening on the boundary. In this one, I think there's definitely going to be a chance for us to say, And so let's not rush ourselves. Let's enjoy the process. So on the boundary, what's true? We have x squared plus y squared equals 4, because that's the bounding circle. Now, remember the goal. When we're working on the boundary, what we want to do is we want to reduce our function to a function of one variable. Look at our function. See, our function, h of xy, looks like 2x cubed plus 3y squared minus 12x. And now we say, can we use the fact that we're on a boundary to knock it down to one variable? And I claim, yes. Because what do you see? There's only one y, and it happens to be a y squared. So we say, oh, that's y squared. I can replace y squared by 4 minus x squared. So we have that on the boundary, this becomes 2x cubed plus 3 times 4 minus x squared minus 12x. Or 2x cubed minus 3x squared minus 12x plus 12. Now we have it down to one variable. And this is a good time for us to say, there's got to be something happening here. And there is something. There's a little bit more of a subtlety here. So let's not rush. Let's pause. Is there anything else we need to add to what we've just said? Think about the picture. Look at it. If you look at this function, what's true? Say, look, that's a great function. I love that function. I can plug in anything and life is good. But look at our picture. We can't take arbitrary choices for x because we're constrained by the fact that we have to be in the circle. So we do have this function with the additional constraint that says, look, we only go between -2 and +2. So on the boundary, it's this function for -2 less than or equal to x less than or equal to +2. So now what we're really trying to do is optimize this function over this interval. Well, all right, so what do? Take the derivative, 6x squared minus 6x minus 12, set that equal to 0. Well, all right, you can factor out a 6, x squared minus x minus 2 equals 0. And you can keep factoring, because that looks like it should factor nicely, because, well, it does factor nicely. Almost like they wanted us to have a nice problem. Two things that multiply to -2 add to -1 would be -2 and +1. And so we say, aha, that leads us to several possibilities, namely that x equals 2 and x equals -1. Now, one other thing we need to throw in there is we should also throw in x equals -2. Why should we throw it in? Well, because that's a boundary point for this one-dimensional constrained optimization. And so you should throw in the boundary points there. So in some sense, this is a boundary in 1D. Now, 2 and -2, those are actually pretty easy to spot. So that's 2, and that's -2. And on a side note, if you're thinking about it, if you're worried like, the worst case scenario is you're testing more. And you're like, if you're not certain whether or not you should throw a point in, if you throw it in anyways, you'll still be finding the absolute max and absolute min. It'll just have said, look, I'm going to do more work. Because if it's one thing I like, it's more work. Well, maybe you actually don't like more work. And but in terms of the actual process, you're better off checking more if you're and be certain than checking less and being like, I'm not really sure. So we want certainty. We want to make sure that we have our answer. We still have to finish up though. We have x equals -1. Now that means what? Well, we're on the boundary. So if x equals -1, 1 plus y squared would equal 4, or y squared equals 3, or y equals plus or minus √3. So we get a few more points. -1 √3, -1 minus √3. Okay. So that would be here and there. All right. So there we go. We are ending up with 6 points to test. And once we plug those points in, and we can find our answer. We've made our list. Good. So it says, look, we can handle curves which aren't flat. We can handle all sorts of curves. Now you might have said, but Steve, you took advantage of the fact that you could rewrite the function using the boundary curve. What if you couldn't have done that? Well, if we couldn't have done that, here's what we would have done. And so this is just sort of a side note. Here's an alternative of what we could have done. What we could have said is like, hey, if I want to parameterize the boundary, I can do it because it's a circle. And circles are easy to parameterize. Namely, it's a circle radius 2, so it'd be as 2 cosine t, 2 sine t. And so, as you let t vary, that goes around the whole boundary. So, you could now plug that into h. So h of 2 cosine t, 2 sine t would be h as a single variable, as t. Now, optimize, because you're down to one variable. And then we can say, okay, one variable optimization, and that will give us what happens on the boundary, where we need to look. So if we hadn't had a way to say, oh, we can clean up and rewrite, we still have alternatives. So there we go. There's also other interesting things that we can do, and we'll get into this in another session. Because you're like, ooh, we can learn more? Yes, there's always more to learn. Isn't it great? Just when you thought you've learned it all, and it's like, one more thing. Okay, so let's plug all of these points into our function h. And be patient. Be the right amount of patient. The good news is a lot of them are on this line where we have y equals 0. So it's not too bad to compute. So for instance, 2, 0. Well, that's 2 times 8. That's 16 plus 0 minus 24. 16 minus 24 is minus 8. Negative 2 times 0, well, that would be minus 16 plus 24. That would be positive 8. Okay, well, how about root 2? So we have 2 times square root of 2 cubed. Okay, so if you have 3 square root of 2's multiplied together, if you put 2 of the square root of 2's together after 2, there's one more square root of 2 left over. So 2 times square root of 2 cubed becomes 4 root 2. Then you have minus 12 root 2. So that would be minus 8 root 2. Okay, so that's if you plugged in root 2. So minus 8 root 2. If you plugged in negative root 2, it would change your sign. So it would become minus 4 root 2 plus 12 root 2. And so therefore, we'd end up with positive 8 root 2. Which leaves us with these points. When you plug in x equals negative 1 and y equals root 3. Now notice, we can do them both at the same time because the only place where y shows up is we square it. And so, what do we have? Minus 1 cubed is going to be minus 1 times 2. So that's minus 2. Y squared is 3. So that's 3 times 3, 9. Okay, so we have minus 2 plus 9, that's 7. And then minus 12 times minus 1 is positive 12. So that's going to be, again, minus 2 plus 9 plus 12. Great. Oh, those are nice numbers. 19. 19. Great. Well, and that's for either one. Now, one thing you might be wondering about, how does 8 times square root of 2 compare to 19, right? Because that's sort of like, well, we're pretty confident that root 2 is bigger than 1. So 8 times root 2 is certainly bigger than 8. But actually, we don't even have to think very hard. Because we say, hey, 8 times root 2 is below 2, right? All right, root 2 is below 2, yes? Square root of 2 is smaller than 2? Okay. So 8 times square root of 2 would be smaller than 8 times 2. So 8 times square root of 2 is below 16, which is definitely below 19. So what does that tell us? Well, we can now say, look, our max is 19. Is it okay that we got the max at 2 different places? Yeah, we're okay with that. Good stuff. It's all right that we get the maximum value in 2 locations. You're allowed to attain the maximum value at multiple locations. The min? All right. Well, for that, we say, okay, the smallest value is this one, minus 8 root 2. And there we go. So we go between minus 8 root 2 for the minimum value and positive 19 for the maximum value. And we can mark it. Our min is here in this corner, and our max is at those locations. All right, great, cool, good stuff. Wonderful stuff, really. All right, well, let's keep going, because I think we have time for one more. It's going to be a little bit similar to one we just did. So our last one, our cool down. Let R be the region bounded by the lines y equals 0, x equals 0, and y equals minus x squared plus 2x plus 3, with corners at 0, 0, 0, 3, and 3, 0, shown below. Wow, they're giving us a lot of stuff. They're drawing us our picture. They're even telling us where our corners are. So let's see, this apparently is at 3. This one here is at 3. This one's at 0. And what's the problem? Find the minimum and maximum values of the function x squared minus 2x plus y squared minus 4y plus 3. Okay, well, let's work through it and see what we have. Okay, so let's start with the interior. So we're making our list. And we'll probably a lot of points on our list. So on the interior, our function, well, where's our function? There it is. It's f. So we're going to set our gradient equal to 0. So this is our interior. And what happens here? Well, we're going to have f sub x, 2x minus 2 equals 0. F sub y, 2y minus 4 equals 0. Okay, well that's pretty straightforward. We can read it off, right? That says x equals 1 and y equals 2. We check if it's on the domain, or rather it's in the domain, and we can really, because of this nice grid, we can say, look, it's right there. That's in. All right, because, you know, as I say, in one point you're in, and the next point you're out. So we want to make sure we're in, right? Okay, so from here, we throw in our corners. Okay, so we'll just do that. 0, 0, 3, 0, 0, 3. All right, that leaves us with 3 bounding curves. 2 of them I think are pretty straightforward, and namely the bottom side and the left-hand side, the bottom and the left. So let's do the straightforward ones first. The bottom curve, that would correspond to when y equals 0. So for the bottom, we get our function is really f of x comma 0. Well, that would be x squared minus 2x plus 3. Take the derivative, set it to equal to 0, and we get x equals 1, which says that point. There we go. So that's on our list. Whoops, I forgot my parentheses there. So 1, 0. Good. Now let's go and do the left-hand side. So what's happening there? On the left-hand side, that would be where x equals 0. Okay, so for the left, our function becomes f of 0 comma y. All right, well that's easy. So the first terms drop out, and we get y squared minus 4y plus 3. Take the derivative, single variable function, 2y minus 4, set equal to 0, we get y equals 2. Which would mean at x equals 0, y equals 2. That's here. That's in our domain. So that makes our list 0, 2. Which leaves us with one more part we have to work on. Okay, so the last part for us to work on is the last curve, which is that parabola. Okay, so we're going to have to think about that a little bit. Well, it's nice to have something to think about. We don't want to be doing math mindlessly. That just sounds boring. It's fun when we get to think about stuff. Okay, so on the parabola. Well, keep in mind that that parabola is what? It's this curve. It's y equals minus x squared plus 2x plus 3. So one thing we can think about is we can say, hey, how can we use the fact that we're on our bounding curve to get down to a function of one variable? Now, one thing we could do if we were crazy is you could say, perfect, look, just plug in minus x squared plus 2x plus 3 in for y and expand, and then you get like a fourth degree polynomial, and like, wow, and it could work. It could actually work. But before we start going like crazy, let's see if we can say, oh, is there something more subtle? We want to get to the point where like, hey, we want to be able to pick up on interesting approaches. All right. So let's take a look. What do we see here? We really want to focus on our function and say, do we see a piece of our bounding curve showing up in our function? And can we use that to knock out variables? Well, the x squared minus 2x is essentially the same as minus x squared plus 2x, just off by a sign. That says I can replace on the bounding curve, that's the parabola, this piece by something very nice. In particular, this says x squared minus 2x is the same as y, gotta be careful here. So I'm gonna move this, move that. So it's gonna be 3 minus y. There we go. Yeah, because we move these terms across, move the y across. So I can replace x squared minus 2x by something really clean. So we can say, look, our function on the boundary becomes that 3 minus y plus y squared minus 4y plus 3. Okay, well, that's wonderful. Why? Well, what do we end up with? We can say, look, this is y squared minus 5y, and once we have that, okay, plus 6. Okay, so that's what we have on the boundary. All right, well, take the derivative. 2y minus 5, set it equal to 0, y equals 5 halves. Okay, so y equals 5 halves, where would that be? Well, okay, so where is 5 halves? It's at 2.5. So that would tell you that is where you need to look. Okay, good. Now, you might also be saying, hey, wait a second, shouldn't you also put some additional constraints about where y can go from? So, for instance, we say, look, y squared minus 5y plus 6, sure, but y can't be arbitrary because I have to have y ranging over this region. So the largest y could ever be is up here at the top. So should we check that point as well? And that's actually a reasonable thing to do. So if we say, okay, just because we rewrote our function, there's also some constraints on the places where y can go. And so we really should have said, well, look, this is going to be the fact that y has to be below 4. So we should also include the top point to check as well. All right, so Well, where's that top point? That's at 0 and 4. So there we go. And we didn't mark down. There's this other point, 5/2, comma, something. I'm not going to work out the something yet. Okay, I'm going to go right into evaluating. So this is at the point 5/2, comma, something. We'll come back to what that something is, because we're not actually after the points. We really just need to say there is a point, and what's the value of the function at that point. We can probably figure that out without even knowing what the coordinate is. Oh, I can already see I goofed up. This is at something, comma, 5/2. Not 5/2, comma, something. So something, comma, 5/2. Okay, so we're plugging each one of these points into our function f. And we will see what comes out. Okay, well, let's start with our classic 0, 0. When we plug in 0, 0, what do we get? 0, there it is, 0, 0, 0, 0, 3. 3, good. Okay, how about 1, comma, 2? Okay, that'll be 1 minus 2, that's minus 1. And then we'll have 4 minus 8, that's minus 4, minus 1, minus 4, and plus 3. So that's negative 2. Okay, all right. So negative 2. 3, comma, 0. Well, what is that going to be? Well, okay, if you plug in 3, comma, 0, well, we can actually just come into here and plug in 3. 9 plus 12, 9 plus 3 is 12, minus 2 times 3 is 6. 0, comma, 3, plug 3 into there. 9 plus 3 is 12, minus 12 is 0. 1, comma, 0. Okay, come into here, plug in 1. 1 minus 2 plus 3, so that's 4 minus 2 is 2. 0, comma, 2. 4 plus 3 is 7 minus 8, negative 1. All right. 0, comma, not 0. 1, comma, 4. I'm so sorry, because that's the top. All right. 1, comma, 4. Well, what would that be? Well, it's like we came into our parabola and we said, look, plug in our 4. So that's 16 minus 20 plus 6. Okay, well, 16 plus 6 is 22 minus 20, and would leave us with what? Leave us with 2, right? I think so, yeah. So 2. Okay, good. Now, this last point. Well, again, we don't know what the x is, but we say, look, it's on our parabola, and we know what our function is as a function of y. So we can plug in the 5/2 into there. So let's see, 5/2 squared, 25/4, minus 5 times 5/2, that's minus 25/2, and then plus 6. Well, all right. So this is really, in terms of force, it would become what? 25 minus 50, and 6 is 24 over 4. And so we get 49 minus 50 over 4, so that's negative 1/4. And now we're ready. We can read off our answers. And what do we end up with? Well, we scan, and we say, where's the largest? Well, 6. Okay, good. So our max is 6. Where's the smallest? Well, negative 2. So our min is negative 2. And we're done. Okay, now that we finished it, let's point out something we could have seen earlier on, and then we could have said, oh, we can check our answer. Because this is actually, there's a way we could have rewritten this function. We could have said, okay, x squared minus 2x, and let's complete the square. So that'd be plus 1. And then y squared minus 4y, and again, let's complete the square, plus 4. Well, here I have 1 and 4, which gives me 5, but I should have 3. So subtract 2. So our function is really x minus 1 squared plus y minus 2 squared minus 2. Now what's the point? Well, think about what this is really measuring. It's looking at our distance to the point 1, 2 squared. Because if you see x minus something squared and y minus something squared, that's like a distance formula. So really our function is based off of how far away you are from the point 1, 2. So it's not surprising that the smallest we can get is at 1, 2. And the largest we can get is over here in this corner, because this is the furthest corner away from the point at 1, 2. Everything else is closer to our point. So if we had been able to spot, oh, hey, by the way, our function has this nice interpretation, and so geometrically I know it's smallest where we're comparing it to the point 1, 2, so it has to be the smallest at 1, 2, and it's largest the farthest I am away. Now we could only do this because we had, an x squared minus ax and a y squared minus by. If we had even just a little change, so like a 2y squared and an x squared, forget it, out. All right, you have to be more careful. Or we had an xy, careful, crazy stuff can happen. But it's nice to say, okay, the geometric intuition matches with the work we did. Well, what a set of problems. It doesn't feel like we did very many problems, but it also feels like we did a lot of work. And that's because these problems are ones where each individual step does take work. So keep at it, keep doing the work. You'll get better, it'll come, but it takes time. So don't rush yourself and just be kind to yourself. Take as much time as you need to figure it out. You've got plenty of time. Okay, hope to see you again.